Hello students, I welcome you all to the lecture series on control system. Control system subject is basically defined into three categories. First is representation of system, second is analysis of system, and third is design of controller or compensator for the system. Generally, in GATE 10 to 14 marks question will come from this subject. Representation of system can be done by four ways. First is mathematical modeling, in which differential equations have been used to represent a system. Second is block diagram representation. Third way is using signal flow graph. In both two representation, transfer function is being used. And the last one is state space model. So these are the four ways in which a system can be represented. Next is analysis of a system. There are two approaches to analyze a system. First is time domain approach and second is frequency domain approach. In analysis of a system, we will analyze the transient response of the system, steady state response of the system, as well as the stability analysis of the system is also being discussed. In the third part is controller and compensator design will be discussed. In controller, we will discuss P, I and D controller, proportional, integral and derivative controller and combination of these three. And in compensator design, we will discuss lag compensator, lead compensator and lag lead compensator design. Now we will discuss some of the basic terminology in control system. So let us discuss what do you mean by a system. Or we can say system as a plant, and you will find in some cases it is also represented as process. So all these can be termed as same. So a system can be defined as a collection of components which are connected together to perform a task. And the difference between the control system and a system is, if the system is able to give the desired response always, then we will say it is a control system. So if a system always gives desired response or output by manipulating its input, then we can say it is a control system. Generally, a control system is basically categorized into two. First one is open loop control system and second one is closed loop control system. So we can categorize control system in two parts. First is open loop and the second one is closed loop control system. In open loop control system, there is no feedback. So from output, we are not taking any feedback in open loop control system, or we can say there is no effect of output on input. No effect of output on input of the system. A block diagram representation of the open loop system is shown to you. This is a plant and we are taking output from the plant. A controller is connected which is giving actuating signal to the plant based on the reference input. So we can observe that we are not taking any feedback from the output, or there is no effect of output on the actuating signal of the plant. So controller is designed in such a way that from the reference input it will generate the actuating signal which is acting on the plant so as to give the desired output. This is open loop system representation. Now let us discuss some of the example of the open loop system. First, I will take the example of a washing machine. In washing machine, what we do is we took the cloth and put it in the washer and set the timer. Or in some of the automatic machines, you will set the type like cloths are woolen or gentle or cotton. So according to that, you will set the timer of the washing machine. Output is cleanliness of the cloth. But you are not taking any feedback from the output. That is, you are not measuring whether the cloths are properly clean or not. You are just setting the timer and you are getting the output, that is the cloth after washing. So it is the example of an open loop system because we are not taking feedback from the cloth, that is whether they are properly clean or not, and we are not giving any input based on this output. So this is an example of a open loop system. Similarly, if I am having a room heater, without temperature measuring device, then this is also an example of open loop system because it has to do the task of heating the room only without taking the actual measurement of the room temperature. So it is also an example of a open loop system. Now I will discuss closed loop system. So as I already told you that in open loop we are not taking any feedback from the system, but as in closed loop system we are taking feedback from the system. So it is also known as feedback system. So I have taken a block diagram representation for open loop system. This is the plant. This is the output of the plant. A controller is connected to the plant. Which is giving actuating signal to the plant. We are taking output of the plant and giving it to a feedback element. And I am comparing this with the reference input. And now in this case, error signal is being given to the controller. And based on this error signal, actuating signal is generated from the controller and this is going to be given to the plant. Whereas in open loop system, there is no such error signal present. We are only giving the reference input to the controller and from that the actuating signal is generated. This block is known as error detector. So, one of the basic examples for the closed loop system is traffic light based on density of the traffic. There are two types of traffic light exist. One is which works on the time setting. So it will automatically turn red light on for 15 seconds and then green light will be on for 10 seconds. That is based on time setting. But if the traffic lights are designed based on density of the traffic, so if there is too much crowd on the road, then it will automatically increase the timing of red light so that the crowd is managed. So if the traffic light is designed based on the density of the traffic, we can say it is an example of closed loop system. Along with that, automatic car is also an example of closed loop system because automatic car will detect whether to stop or reduce the speed according to the road condition. Now I will discuss the mathematical modeling. Most of the physical systems can be represented by its mathematical modeling. We are going to discuss mathematical modeling of two systems. We will take mechanical systems and I will also tell the mathematical modeling of electrical systems. In mechanical systems, we are taking two types of models. First is translational and second one is rotational motion. So translational motion means which moves in a straight line only. So the mechanical system can be classified into two ways, translational motion and the rotational motion. The differential equations developed for the mechanical system are based on Newton's law. So for translational system, Newton's law states that algebraic sum of force acting on a body is equal to mass into acceleration. This acceleration is first derivative of velocity, so it can also be written as m dv by dt, and in the term of displacement we can write it as m d2x by dt2. Whereas in case of rotational motion, Newton's law states that sum of torque exists on a body, algebraic sum of torque exists on a body is equals to the moment of inertia into angular acceleration. J is moment of inertia, A is angular acceleration. This angular acceleration can be written in angular velocity term as d omega by dt and in angular displacement form as d2 theta by dt2. And in electrical system, we will use KVL and KCL, Kirchhoff voltage law and Kirchhoff current law, to determine the mathematical model of a electrical system. Before discussing the mathematical modeling, let us compare the open loop system and the closed loop system. So first thing is, open loop system are simpler and inexpensive because less number of components are required to design a open loop system, whereas closed loop system are costlier and complex because number of components involved in the closed loop system design are more. We have to feedback output and then compare it with a reference signal to generate the error signal. That's why it is costlier and complex. It consumes less power, whereas closed loop system consumes more power. Because to generate an error signal, we have to measure the output at every instant and feedback it to the error detector, so it consumes more power. Closed loop systems are inaccurate and unreliable because if there will be some disturbance or noise exists in the system, then the open loop system will not give the desired actual result. So they are inaccurate and unreliable. They are sensitive to noise or disturbance. Whereas closed loop systems are more accurate and reliable. Insensitive, or we can say less sensitive to noise or disturbances exist in the system. If there will be some disturbance or noise exists in the closed loop system, then also the closed loop system will give the desired response. Last is, stability is not an issue in open loop system because generally all the open loop systems are stable, whereas stability is a major issue in closed loop system. We have to properly design the system such that it will not lead to unstable system. These are some of the basic differences between open loop and closed loop system. Now let's move on to the mathematical model of translational motion. So just like an electrical circuit, we can define any electrical circuit using three components. The three components are resistor, inductor and capacitor. This is energy dissipating devices and these two are energy storage devices. Inductor always stores its energy in magnetic field, whereas capacitor always stores energy in electric field. In the same way, translational motion of a mechanical system is also represented by three elements that are mass, second is damper, and third is spring. In translational motion, input is always force and output is linear displacement, which is generally represented by x of t, or linear velocity, which is represented by v of t. So let us take the first element, mass. Mass is generally represented by a rectangular block M. It stores energy in kinetic energy form. So it always stores energy in kinetic energy form. Because we require three elements, two elements to store energy and one element to dissipate energy. So mass is the element in mechanical system which stores energy in kinetic energy form. Its one end is connected to a reference. So this is a reference. And to another end, we are applying a force F of t to it, due to which there will be some displacement and there will be some velocity in the mass. So we can represent, according to the Newton's law of motion, force acting on a mass is equals to m into a, which can also be written as m dv by dt, or in displacement form it can be written as m d2x by d22. The next element I am going to take is damper. So damper is the element which represents friction in the system. So it is also an energy dissipating element, just as resistance in electrical circuit. Friction always occurs when there is a relative motion between two elements. Generally, friction is classified into three. First is Coulomb friction, second is viscous friction, and third is stiction. Friction always occurs when there is a motion or there is a relative tendency of motion between two physical elements. So first friction I am discussing is Coulomb friction. It always occurs between two dry surfaces. Viscous friction is due to liquid. Like if there is a cylinder and this is a piston, and if you are applying a force on it and this cylinder is filled with some oil, then due to this oil there will be some frictional forces exist on this piston. So this friction is known as viscous friction, and static friction is between two contacting surface to initiate the motion. That is, if their system is at rest, and to initiate the motion, so the friction which is occur at the rest is known as friction. So the damper is represented as this. We have taken damping coefficient as F, and these are two nodes of this damper element. I am applying the force F of T to this node, due to which there will be some displacement x1t and some velocity v12 at this node. Their displacement is x2t and velocity is v2t. In some cases, you will find that the second node is reference node. In that case, x2 is equal to 0 and v2 is equal to 0. If we apply Newton's law of motion to it, the force acting on a damper is equal to F v1 minus v2. Or in the term of displacement, we can write it as F, as velocity is dx by dt. So we can write it as F d by dt x1 minus x2. Now I will discuss the third element, that is spring. So it stores energy in the form of potential energy. So now we have three elements. One is dissipating element, that is damper, and another two are energy storage element, that is mass and spring. Same as in electrical circuit. So spring stores energy in the form of potential energy. So I have defined this, design a spring whose spring constant is K. If I am applying a force at this node, so displacement will be occur at this node x1t and some velocity is v12 at this node. Displacement is x22 tt and velocity is v2t. So according to Newton's law of motion, force developed by the spring is K x1 minus x2. Just keep in mind this, that the force developed by the spring or damper is always opposite to the displacement acting on the spring or damper. This should be kept in mind always, because it will require when we will draw free body diagram. So now let us take a simple translational system. So I am taking a simple translation system. This is the reference. A spring and a damper block is connected to the mass m. Spring is having a spring constant of K and damper is having the damping coefficient of F. A force F is applied to the mass m and the displacement x is going to take place. So how to write a differential equation for this system? What you have to do is, you can make a free body diagram for it. So I am taking mass and I am applying the forces acting on the mass. So I can see that forces acting on the mass in this direction. So This is the force acting on the mass. So, because of the spring and the damper element, some forces are acting on the mass also. So, as I already told, that force developed by the spring is always opposite to the displacement. So, because displacement is in this direction, upward direction, so the force acting by the spring on the mass is in this direction, which can be written as kx minus 0, because it is reference and it is x. So what we have discussed is kx1 minus x2. So we can write it as kx minus 0. In the same way, damper element will also act the force in the direction opposite to the displacement. So we can write it as f dx by dt only, because it is also connected between x and reference 0. So we can say that sum of force acting on the block of mass m is resultant forces F minus, because we are taking this direction of force is positive and this is acting opposite direction, so we can write as minus sign here, minus kx minus F dx by dt is equals to m into a. I am writing a as d2x by dt2, so we can write F is equals to m d2x by dt2 plus f dx by dt plus k into x. This is the differential equation for the translational system as shown to you. This is the free body diagram for the translational system. We can also represent the system using mechanical network. For that, what you have to do is, you just have to identify the principal nodes. Principal nodes are always equal to the number of displacement. So we can observe here that there is only one displacement. So there is one principal node which I will mark as x and take one node as reference node. So this is my reference node. Now just always take mark connected between principal node and the reference. So I am taking a marks block M and connected it between principal node and reference. Now I can see that the spring is connected between this principal node X and reference node 0. So I have connected a spring K between the principal node and the reference node. In the similar way, damper element is also connected between principal node and reference. So I will write a damper element between principal node and reference. Just you have to make in mind that force always acts between principal node and reference node. So I draw a force block F to the principal node and reference node. So this is the mechanical network for the translational system. Now you can define this M. F equals to m d2x by dt2 plus k into x plus f dx by dt. Because it's just like a current source, it is divided into 3 parts. Now I will discuss about the rotational motion. Mechanical system which does rotation. Motion is always about a fixed axis. In In mechanical rotational system, input acting on the system is always torque because we are talking about the rotation, and output is angular displacement, or you can say angular velocity. We represent angular displacement as theta t and angular velocity as omega t. Just like electrical system and mechanical translational system, three elements are required to represent any mechanical rotational system. The three elements to represent any mechanical rotational system are: first is inertia, second is damper, and third is torsional spring. Similar to electrical system, one is energy storage element, two are energy storage element and one is energy dissipating element. Now let us take first element, that is inertia. Inertia, just like mass, stores energy in kinetic energy form. So inertia is represented by J, and its one end is generally connected to a reference, and to another end I am applying a torque which is equals to P. Because of the application of torque, there will be some angular velocity and angular displacement theta. So according to Newton's law of motion, the torque developed is equals to J into alpha. Alpha is angular acceleration. So the torque is equals to J d omega by dt, or we can write it J d2 theta by dt2 in terms of angular displacement. So due to inertia block, we can observe the second order differential equation. The next element is damper. It is just like as in the mechanical translational system. So as in mechanical translation system, it is energy dissipating element. So in this case also, it is energy dissipating element. It represents friction in the system in the same way as in mechanical translational system. So we can represent damper as this block. Damping coefficient is F here. Now I am applying a torque T on this node. Because of this, there will be some angular displacement omega 1 and angular velocity omega 1 and angular displacement theta 1. At this node, angular velocity omega 2 and angular displacement theta 2. So on applying Newton's law of motion, torque developed due to damper is F into omega 1 minus omega 2. F is damping coefficient, or we can write in the term of displacement as F d by dt theta 1 minus theta 2. Now let us discuss the third element, that is torsional spring. You can relate it with the shaft which is coupled between a motor generator set. You have observed a motor generator set in which there is a shaft. So the torsional spring represents that shaft only. To represent the torsional spring, we will take a spring only and spring constant is K. On the application of torque to it, there will be a angular velocity and angular displacement omega 1 and omega theta 1. Similarly, at another end, omega 2 and theta 2. The torque acting on it is equal to K theta 1 minus theta 2. So now we have two energy storage element and one energy dissipated element. So we can represent any mechanical rotational system using these three elements. So let us take I have taken a shaft which is coupled with a rotational device. So because of this shaft, as I already told us, shaft is same as a torsional spring. So shaft is having some spring constant K, and this is a block which is having some inertia which is rotating J, and because of this surface there will be some friction whose friction coefficient is F. So I am applying the external torque on it. So this is a disc. It is initially at this position. On application of torque, it has moved to some angular displacement theta. So we can observe that torque is acting in clockwise direction, whereas just as in the case of translational system, due to damper and spring, torque always exists opposite to the direction of displacement, just as the same in mechanical translational system. So if angular displacement in clockwise direction, so because of this friction, the force developed by this friction is in opposite direction, which is equals to F d theta by dt, and in the same way the force developed by this shaft is in the opposite direction, that is K theta. So the torque, resultant torque acting on the disc is T minus F d theta by dt minus K theta is equals to J d2 theta by dt2. So we can write it as T equals to J d2 theta by dt2 plus F d theta by dt plus K theta. So it is a second order differential equation. Now I will take the electrical system, how to represent the mathematical model of an electrical system. First I am going to take a series RLC circuit. So I have taken a series RLC circuit. A voltage V is applied to the circuit. Because of the application of voltage, current starts to flow. So I have assumed that I current is flowing to the circuit. On applying KVL to the whole circuit, I will find out that V is always equals to voltage across resistance plus voltage drop across inductor plus voltage drop across capacitor. So we can write it as voltage across resistance is always equals to I into R. You all know that. Plus voltage developed in the inductor is as di by dt. This also you all know that. And the capacitor voltage is 1 by C integral I dt. You can see here that this equation contains differential term as well as integral term. But we want whole equation in the term of differential form only. So you also know that I is equals to dq by dt. Q is here charge. So we can write as Q equals to integral I dt. So by replacing integral I dt with Q, we will find out the equation is V equals to, we will write whole equation in the terms of Q only. So I can be written here as dq by dt here. So we will write it as R dq by dt plus L d2q by dt2 plus 1 by C into Q. So we can observe that this equation is now in the second order differential form only. So in this way, an electrical circuit can be represented using mathematical model. Now let us take a case of parallel RLC network. So now I have taken a current source I, which is driving current into a parallel RLC network. So we apply KCL at this node. The current is divided into three parts, I1, I2 and I3 here. So we can write as I is equals to, and we are taking this voltage across the capacitor is V. So the current in the resistance is, because these three are connected in parallel, so the voltage across all three elements is V only. So the current through R is V by R plus the current flowing through the inductor is 1 by L integral V dt. As you know that VL equals to L di by dt. So I is equals to 1 by L integral VL into dt. And the current flowing through the capacitor is 3 dV by dt. Now we can again see that this equation is containing differential term along with integral term also. So to convert it into differential form only, we will apply the Faraday's law of electromagnetic induction, which states that voltage induced is always equals to rate of change of flux. So we can write as phi equals to integral V dt. Substitute this in equation, we will find that I equals to, we replace V by d phi by dt. So 1 by R d phi by dt plus 1 by L into phi plus C d2 phi by dt2. You will find out that this equation is only containing the differential terms only. So it is second order differential term. So we can formulate any electrical system either using this representation or the representation I told you before. Now we will find some analogy between all four systems. I am writing all four equations for all the four systems. For the mechanical translational system, F is equals to m d2x by dt2 plus f dx by dt plus k into x. For mechanical rotational system, we have find out that torque developed is j d2t theta divided by dt2 plus f d theta by dt plus k theta. Whereas for electrical series circuit, V is equals to L d2q by dt2 plus R dq by dt plus 1 by L q. Similarly, for parallel circuit, I is equals to C d2 phi by dt2 plus 1 by R d phi by dt plus 1 by L phi. These all we have find out already. So now I am going to find out the analogy between all four systems. So let us now try to find out the analogy between all four systems. So this is translational system. This I represent the rotational system. This electrical system when elements are connected in series, and this is the electrical system when elements are connected in parallel. And current source is there and voltage source is there. So you can relate from these equations that in translational system the force acting is F, whereas in rotational system it is T. In electrical series system it is V, and electrical current system it is I. In the same way, you will find out that M is related to C here, J in rotational system, L in electrical series system, and phi is related to X. In rotational system it is related to theta. In electrical system it is related to Q. 1 by R in this system is related to F. In rotational system it is also related to F, whereas in electrical system it is related to R. And the last element we have is 1 by L. In electrical system is when they are connected in parallel is related to K. In rotational system it is also related to K, whereas in electrical series it is related to 1 by L. This analogy is known as FTV analogy, whereas this analogy is FTI analogy. Force torque voltage analogy, and this is force torque current analogy. Now let us take an example of a complex mechanical system to find out the mathematical model of a system. So this is a reference. So to begin with the complex system, we have to capture few things in the mind. First thing is, you just have to identify the number of principal nodes. What do you mean by principal nodes? Principal nodes are always equal to number of displacements. So now let us take an example which makes you more clear. So there are two springs, one damper, a mass block M. A displacement of x1 will occur in the mass M block here, and at this point you can see a displacement of x2. This spring constant K2 and this spring has the constant K1, and this damper has a constant of damping constant F1. Now you can observe here in this complex system the force acting on the system is 0. So we are not applying any force on the system. What you have to do is just you have to make a mechanical network of it. So to make a mechanical network, you just have to identify the principal nodes. We can observe that there are two principal nodes exist in the system because there are two displacements. So there are two principal nodes, and what you have to do is you have to make a one reference node. So I make one reference node and two principal nodes. Mass is always connected between principal node, the node which is connected to the mass, and the reference node. So we can connect mass M between x1 and reference. Now we can see that this spring having the constant of K2 is connected between x1 and this is the reference 0. So I am going to connect a spring K2 between x1 and reference node. Now we will see that this spring is connected between x1 and x2. So these are two nodes. Now we connect the spring between two principal nodes. So always keep in mind that mass is always connected between a principal node and a reference node, where a spring can be connected between a principal node and a reference node or between two principal nodes. You can see here also. We can observe that this damper element is connected between x2 and 0. So we can connect the damper element here, which is represented as F1. So this is the mechanical network formulation for the whole system. There is no force acting on the system. If there is any force, it's like if I assume that a force F is also acting on the mass, this. So we always connect force between the principal node and the reference. So we connect a force block here between principal node and reference node. But now there is no force here, so we have eliminated. What you have to do now to develop the differential equation, you just have to apply differential equations at each node. So if I see at node 1, this is my node 1 and this is my node 2. So at node 2, you can see that there are two elements, K2 and F1, whereas at node 1, there are three elements, M, K2 and K1, two springs constant. And the net force acting on the system is 0 here. So what we can write is, because of mass block M, we can write the force due to the mass block is M d2 x1 by d2, because it is connected between x1 and 0, plus due to the spring, it is K2 and it is x1 and 0. So we will write it as x1 minus 0 plus there is another element which is connected. So this is K1. So it is connected between x1 and x2. So we have to take into account this also. So just you have to take this as higher potential, just as in the case of nodal analysis also. So I am applying the force due to spring is K1 x1 minus x2 and the net force is 0 here. So first equation for the mathematical modeling of the system is M d2x by x1 by dt2 plus k2 x1 plus k1 x1 minus x2 equals to 0. Now I have to develop second equation at node 2. So at node 2, you can observe that there are only two elements. First is the spring element K1 and second is the damper F1. So taking node 2 for the nodal analysis, this is F1, this is K1. So at node 2, the second differential equation form is, we have seen that one is damper element. So because of damper element, the force is F1 dx1 by dt dx2, because it is connected between x2 and 0. So F1 dx2 by dt2, and another is because of the spring having constant K1. So we will write it as plus K1, and because we are taking this node as reference now for nodal analysis, so we will write it as x2 minus x1 here, and because there is no force acting on the system, so it is equals to 0. So these two are the differential equations to represent this mechanical system. If you want to draw a free body diagram for this system, what you can do is just have to take a mass M, and because of displacement on mass block M is in the downward direction, and as I already told to you that the force developed by spring and by the damper is always opposite to the direction of displacement. So the force developed by spring is opposite to the direction of displacement is K2 x2, and because of this spring is K1 x1 minus x2. So it should be kept in mind that force developed due to spring or damper is always opposite to the displacement. So you know the direction of displacement. So the force developed by the spring having constant K2 is K2 x2 in upward direction. In the same way, the force developed by spring having constant K1 is also in the upward direction, which is represented as K1 x1 minus x2. At this node also, you have to make the free body diagram. So because here in this case also the displacement is downward, so the damping force existing on this system is F1 dx2 by dt, and another due to spring constant is K1 x2 minus x1. So this is the free body diagram representation, and this is the mechanical network to formulate the differential equation at each node. In the next class, I will discuss with you the transfer function. What do you mean by transfer function? How can you formulate the transfer function? What do you mean by the characteristics equation? And the block diagram representation of a system. Thank you.